Okay, let me get started. Today is the day the homework 4 is due, the backtracking problem. What I'd like to do, first of all, any questions or comments about the backtracking exercise? Any experiences people want to talk about? Okay, no. What I would like to do is, what I do with this is everybody has to turn in the program and the enough runs to convince us what you did. But I'd like to take the fastest programs in the class and have a bake-off between them. So let's try to decide what the size of program that's fast enough to be interesting. So as I recall, there were two different types of input, right? They were called, what were they called again? What? K and RG. Okay. And I'm going to want to say, if I take for your size, I want the max time for a particular number of vertices to be less than a minute. Okay, so one size might be much easier, one size might be much harder. The size that I care about is the number of subsets. Okay? So you can imagine you may have had a K example with, let's say, 20 subsets, and an RG example with 20 subsets. Not elements, but subsets. And I want to know how fast, I want to figure out what is the size, the number of subsets, for it to be, to separate fast programs from slow programs. Okay, did everybody understand what you do? You have your program, you know how you did on the RG, you know how you did on the K, you know where you started hitting vapor lock and couldn't get further. Okay? How many people's programs here were able to do examples of size 10 or bigger? Okay, almost everybody. That's good. How many people here could do problems of size 20 or bigger? This means that on both the K and the RG for 20, you were able to do it. I'm seeing a bunch of hands still. Okay? Is that a question now or just leftover hands? That's good. Okay? What about 30? How many people could do 30 on both of them? Okay? Now I'm going to want these people to stand up because I can't count very well from hands. If you could do 30 or better on both of them, stand up. Okay? Stand up. Okay? Okay, who of the people that are standing, who could do 40 or better? Keep standing. If you can only do 30, sit down. Everybody here could do 40 subsets or better, okay, or at least who's still standing, who's not tired of standing. Who here could do 50 or more? Keep standing if you could do 50 or more. Okay, let's say if you could do 50 or more on both of them, keep standing. Okay, I'm here seeing 50 or more. The three of you who are standing now, could you all do 50 or more on both of them? Nod vigorously. Oh wait, no. Now I'm seeing someone sit down again. Okay? Who here could do 50 or more on one of them? I see. We got 50 or more on one of them. Okay. Anybody else can do 50 or more on one of them? Now people are standing again. This is nerve. It makes me nervous. Okay. How many people could do 50 or more on both of them? Now I'm down to 2. How many people could do 45 or more on both of them? Is there anybody else? Okay, now I'm seeing somebody up to 3 again. Okay, if you were able to do greater than or equal to 45, okay, on 2 of them, okay, or came so unbelievably close that you're convinced that you should be under this, send me the program. I'm seeing 3 people who are standing now, okay? I don't want to get 100 programs. Is this clear? I want to get 3 programs, okay? So if you could do 45 or more on both of them, and we're close, you know, or we're unbelievably close to that, okay? Oh, it took me 2 minutes instead of 1 minute, okay? Send me the program. Otherwise, so I want to get the programs that were good, and email me them within 24 hours, and I will have my bake-off once I get them. Okay, now people can sit. Okay? Any questions? Okay, and we will talk about how this does after we have our debate. Okay. Okay, what I'd now like to do is to get back to dynamic programming. And the problem of the day involves this kind of, it's sort of a strange looking problem. But it says that we have a certain string processing language that allows a programmer to break a string into 2 pieces, okay, at a cost of n, the length of the string to break it into pieces. And now suppose you want to break a string into many pieces. Can you find the most efficient way to do that? Okay, let's look at let's draw an example here based on what's thing. Suppose I have a string which is 20 characters long. That's what I'm hearing it say. And that you could break after 3 characters. So there is going to be a break here at 3. There is going to be, I think, another break at 8 and another break at 10. Does everybody see that? We want to end up with, if that's true, if we make these breaks, how many string pieces do we have if we make those breaks? 4 pieces. Does everybody agree? And the length of the pieces is going to add up to the length of the original string. And every time you do one of these cuts, the cost is going to be the size of the string that you're cutting. Okay? And the question is to find the cheapest way to do this breakup. Okay? Do people see that the order in which you do the cuts is going to have a different cost? That's the important thing to see here. Right? If we do the cuts from left to right, what's the cost going to be? If we make the first cut here, what's the cost of that cut? 20. Does everybody agree? This is a bad one. I don't like that pen. What if I now make the cut over here? What is the cost of the cut then at 8 going to be after I have made the cut at 3? How much? The string after we've made this cut, what do I know? I've got a bar that goes from here to here. What's the length of that piece? 17. So does everybody agree that that's going to cost 17? Now, once I have made this cut at 8, okay, so now what's the cost of the cut made at 10? 12. Does everybody see that? So that's a cost of what? That looks like 49 to me. Am I right? What if we did this from right to left? What would the cost be? What's the cost of the first cut? 20. What's the cost of the second cut? Second cut is going to be what? This one? What's the cost of that going to be? 10. And once I do that, I'm going to make this cut. What's the cost of this cut going to be? 8. Does everybody see that's 38? Is there any other way we might possibly do the cuts? What other cut could be first? What if we cut it directly at 8? Okay. How much would it cost if I now cut it at 8? This was cutting from the left. This is cutting from the right. What if I did the first did the 8 cut? What would that cost? 20. Then let's say I did the right one. What would this be? What? 8? Right? Because now I'm cutting up this side. Now, what if I cut it at 10? How much is that going to cost? 12. And what's this total come out to? 40. So this was the best one. Does everybody agree that this happened to be the cheapest of the ways of doing it? Okay? The problem in general is to find the cheapest sequence of cuts. Does everybody kind of see that? Okay? Now, so everyone understands the problem, I hope, right? Now, the question is, how do I come up with an algorithm to find the cheapest sequence of cuts? Does anybody see any idea how you might do this? Okay. First, we agree it's a sequence. The order matters, right? Obviously, they're all orders, okay? We could try all n factorial orders, okay, but that's probably bad karma. That's going to be expensive, right? Any idea how we can think about this? Well, if we're thinking about it in dynamic programming, okay, we're going to want to use dynamic programming. Why might this be a dynamic programming problem? Well, if you'll notice, things are ordered from, the input is naturally ordered from left to right. Does everybody agree that there are cuts at different places? Okay. So that's what, to me, when I see something from left to right, I usually think dynamic programming. Okay? But how do we solve this? The first question is, could you come up with a function in English that if I knew how to compute it, okay, I would be able to, as a special case of that, solve the problem that I want? Okay? Can anybody think of a kind of a function that if I could compute it, it would be, it would be helpful? Any ideas? I think, going to work on something. What if I had a function, let me call it C sub I comma j, which is going to be equal to the min cost, the minimum, maybe I'm going to change it a little bit just to make sure I'm clearer about this. What if I said it was the minimum possible cost of partitioning the string between the ith and jth cuts? Okay, let's think about that. Okay, what are the ith and j cuts? Well, on this example, the 0th cut I'd probably say was here. The first cut was at 3. The second cut was at 8. The third cut was at 10. And the fourth cut, just as the boundary condition, was the end of the string. Does everybody kind of get that idea? And now could ask myself, what's the cheapest way to cut up the string between the first and third cuts? Between the first and fourth cuts? Okay? If I had this function, would this be useful for solving the entire problem? How would I use this function to solve my entire problem? Yeah? Does everybody see what this problem is really saying now? Is give me the value of C sub 0, 4, or presumably something like C of 0, n, where n is the number of cuts. Does everybody kind of see that? Okay. This is important. You see how I wrote the function in English? Okay. Now, can anyone give me a recurrence relation for this? Okay. What is a recurrence relation going to be doing? I want to now try to compute what is the cost of Cij in terms of smaller ranges, right? Can anyone give me a recurrence now to compute this thing? Okay. Anyone else to see? We got people alive here? Any ideas? Sometimes you have to figure around with this. Does anyone see a recursive thing going on? A recursive thing is going on when you can solve your problem in terms of smaller things like it. Right? Okay? What's your idea? Okay, let's just think what you're saying here. Okay? Say that again, because I didn't completely know if I agree, if what I want you to say is what you're saying. The minimum, you want to minimize over what? All the possible cut positions, right? Let's say that our cut position was K. Where would K go between? What are the possible values of K that are going to be interesting? 1, 2, and 3? Well, I don't like 1, 2, and 3. Remember, because I'm trying to compute C of ij. So what would be the values that I would want my cuts to take on? Between I and j, right? K could be equal to, what do you want it to be? Between I and j? Okay. Let's write down between I and j. And maybe let's go back to that. I'm not sure I completely like that yet. But what is the cost going to be? The size of the current chunk. That's actually what we need some notation for, right? The cost of that cut is going to be, what if I have to define, it looks like I need to kind of store these numbers someplace, right? That's what's going to define what my sizes are, right? So let me define an array where, let me just say that, just for keeping it someplace, let me say that P of I is going to be equal to the position of cut I. Right? So P of 0 is going to be 0. P of 1 is going to be 3. P of 2 is going to be 8. P of 3 is going to be 10. P of 4 is going to be 20. Do you agree I need to have some way of storing where the positions of the cuts are obviously matters, right? So my notation is now going to be P of I is the position of the ith cut. Now you're telling me the cost if I make a cut at J is going to be the length of the stick from I to J, right? What is the length of the stick from I to J? Okay, if I have the cut from here to here, what is the length of the stick from the first cut to the fourth cut? Yeah? Does everybody agree that it's P of J minus P of I? That is going to be the length of the cut. The cost of cutting the stick, right? Kind of the weight of the stick that I currently have. Okay? So this is going to be the cost of the cut. But once I make that cut, is my problem done? No. What do I still have to do? Yeah? You tell me, plus I've got to recursively do this, right? I've still got, once I make the cut, I now have to solve the problem on the left and solve the problem on the right, right? What is the cost of that going to be? What is the cost of solving the thing? If I cut it at position K, what is going to be the cost of this solving the problem on the left? Okay, ideally someone else. I see these hands are going up, but it's just as true elsewhere in the room. Yeah? Plus the cost from I to K, right? After I've made the cut at K, my left side is a smaller problem. I've got to solve that problem, right? Is there anything else I have to still do? Yeah? Kabunk? Kabunk? Does everybody see that this is the recurrence relation, at least very close to the recurrence relation, that I want? Okay? What is it? What is the next cut that I should make if my stick goes from I to J? I'm going to cut it at position K. Well, what's position K? Well, the cost of it is I pay the cost of the size of the stick, regardless of what K is. And then I have broken my problem into two smaller problems, both of which I can hope to solve by this. Okay? Any questions? Okay? How many people see where this recurrence is coming from? It's not coming from Mars. This is coming, this is a logical thing. There's one thing slightly wrong with this recurrence. And if anybody has anything here that they don't like about it. Yeah? You're telling me K can't be equal to J. Well, what happens if K is equal to J? If K is equal to J, this is going to be empty, right? But what bothers me more is this thing. If K equals J, what is this? C of ik is really going to be what? C of ij, which is what I'm trying to solve for here. So you see that if I try to solve this recursively, I'm going to go into an infinite loop. It's infinite recursion depth. I didn't make the right side get smaller. So how do I solve this problem? Okay, how do I solve this problem? Yeah? Why don't I make it I plus 1 to j minus 1? Does everybody see the same thing happened here? If in fact k was equal to I would be nothing, and this would then be ij. So both of the things are changing. The important point here is that we're going to try every divider between the ith and jth, and the outsides are really just the outsides of the string, and you can't cut there. Okay? Does this recurrence now make sense? Any questions? Are there any basis cases? For recurrence relations, we need basis cases. Are there any values of this recurrence that we kind of know? Okay. Yes? Well, what's the cost of, okay, so that's a good question. You're telling me, I think, that C of I, comma I plus 1 has no intermediate cuts between it, right? And what do you want to assign that cost to be? 0. Let's think about that. I think that that's actually a good case. Okay? What happens, just to make sure we don't get this thing, and the answer is this is good. This is the basis case. What am I a little bit concerned about? I want to make sure if you have a basis case that is always equal to 0, there had better be something that's giving it greater mass later on, right? And the point is that the moment you have something that has more than 2 cuts in it, meaning one real intermediate cut, you're getting into this case and you're going to pay the size of the string, right? So this then I am happy with. Does everybody see why this is kind of the basis case? Okay? That if we have no intermediate cuts, and this is true for all I, between what? 1, and I think it is n minus 1 or something like that. Right? Because again, at the end, we're going to have, at the end, it's going to be n here. Okay, but this piece, if it was just from here to here, it would cost nothing, 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 nothing. Right? Any questions about how this recurrence does what we want? And now we've got a basis case. And the basis case looks like the right answer, because what's going to happen? So long as the range here has, the difference is at least 2, there's going to be an intermediate cut. When the distance between I and k is 1, it means that there's nothing to cut, and we've hit the bottom of the recurrence. Okay? Any questions about this? Okay? Now, what is the running time of this algorithm? Okay? You've got a recurrence. How do I think about dynamic programming? I first come up with a definition of what I want to compute. I then come up with a recurrence relation, including a basis case for it. And what do I now need to do? Once I have that, I ask myself, how do I evaluate this recurrence efficiently? I could have done it by recursion. You could use a recursive program to compute this thing, and it will eventually stop. with the emphasis on eventually. Okay? But is there a way in dynamic programming I can represent this by a table, all the possible intermediate solutions by a table, and then say how many spots in my table and how much time does it take to fill each spot? Okay? What is the table? What is the size of my table C? Okay? What is the size of my table C? If we have a string, basically, where n, we have a total of n, where n, is the highest index. N is not going to be the length of the bar. N is going to be the number of cuts. How big is my table going to be? What? N by n. Does everybody see that the first argument can go between 0 and n? The second argument can go between, I guess, 1 and n, or something like that. Right? This is going to be, the size of C is going to be n by n matrix. And we got to fill out the entire amount for every one of these matrices, right? What is the cost now of filling out every one of these n by n cells? What is the cost of computing Cij if all the smaller values are sitting there waiting in the table? What? You're saying what? Is it constant? Well, looking something up from a table is constant. Looking something up from a table is constant. Looking something up from an array of positions is constant. Constant. Add them up, constant. Min as I goes from j, I minus 1 to j. Is that constant? That is not constant, right? It's going to go, this loop's going to go around how many times? What? How many times will this loop go around? Well, it's going to go around j minus I times, which could be as big as what? What's the biggest possible j? N. And what's the smallest possible I? 0. Does everybody see this loop could spin around n times? So if I'm rounding it up, I'm going to tell you that it's n times m boxes plus n time per box. This is an order n to the cubed algorithm. Okay? Any questions about how I did this? It's not a trivial example, but it is something that you can walk through in a logical way. Okay? And there's a reason for how these things go. Okay? And that's what I'm hoping to try to convince you guys of. Any questions? Any questions about how this problem worked? Or where the n cubed came from? Okay? How many people see it? How many people don't see it? Okay? Any questions? Okay? So this is the design problems, the design way for doing dynamic programming. And I think that, actually it says here, son of a gun, it says that the cheapest, here's how you know I'm right. It said that the cheapest one was n cubed, right? Any questions? Okay, good. So what I'd like to finish talking about today, was not what we just started on last class, was about edit distance. And what was the edit distance problem, just to remind you? You were given two strings, okay? Let's say, what would be two somewhat similar strings? Let's say that we had Stony and Sony. And suppose you want to convert our university to a company. Okay? The edit distance is going to be the smallest number of changes you need to convert one string into the other. In this case, it's relatively simple. By inserting a T into the top string, you would be, either deleting a T from the top string, or equivalently adding a T into the bottom string. Okay, you would be able to convert Stony to Sony. Okay? In general, in trying to convert one string to another, what are two other semi-closely related strings? Just as an example here. I'm kind of drawing a blank. Let's say Steve and sleeve. How do you speak? Actually, let's say Steve and sleeves. Okay, let's get maybe more dramatic here. How would you change Steve into sleeves? Okay, what is the optimal way to do it? I think that the E's, we probably want the E's to match and the S to match, right? There would be a substitute, which would be a T would go to an L. That would be a change. And the V has to turn into an AZ. Does everybody see that? What's the cost of turning a V into an AZ? When I'm allowed to do substitutions, insertions, or deletions, what is the cheapest way to turn a V into an AZ? Yeah? So one possibility is to take this, you're telling me, and insert a Z, and then do a substitute, right? Does everybody see that in two changes, I can change the V to an AZ? And so the cost of turning Steve to sleeves would be 3 changes. Does everybody get that idea? The edit distance problem is given two strings, find the smallest number of changes, okay? In some sense it aligns what parts of the string are the same to focus then on how do you do the transformations upon where they differ, okay? And our goal is for any two strings to find the way that does it with the smallest number of possible changes. Last class, I defined the following recurrence relation, and I want to make sure that everybody accepts this recurrence relation. We're going to let Dij be the minimum number of changes to convert the first I characters of S into the first J characters of T. If I knew how to compute this, if I've got a string that is n characters that I want to edit into a string of length m characters, the answer I ultimately care about is D of mn. Okay, so if I had a function that did this, I could compute the edit distance between two strings. What is my recurrence? My claim is that if you're editing two strings together, the first I characters of one into the first J characters of the other, the cost of this is going to be the minimum of all possibilities. What are the possibilities? To map Steve to sleeves, If the last characters match, we might decide that the cost is going to be nothing for the last match, but then we have to recursively solve a problem on one less top string and one less bottom string. Okay? Suppose we wanted to turn Steve, let's say Steve, let's call it Steve Z into sleaze. The last characters differ. I might choose to substitute a Z for an E. If so, I'm going to pay one change for the substitution, plus I now still have the same recursive problem. The prefixes of both strings have shrunk by one character. And that's why this is I minus 1, J minus 1. I may decide, if it was editing Steve's into sleaze, I may decide I want to add an E at the end of this. Okay? So that I can then match that thing. What would the cost of it be? It could be that if I add a E at the end of that string, it's going to be so I can match it on the other string. If I am, that's going to correspond to this case. If I insert a letter at the end of S, I pay 1 for that insertion, and what's left is I still have the full original top string, which is why that's I, but now it's going to match the last character of the other string. The other string has shrunk by Z minus 1. Or I might decide to delete a character, get rid of the Z here. In which case, if I delete it, I pay 1 for deleting the character. My top string is 1 shorter, and the bottom string is the same size. Does everybody see that if I have this recurrence, that this recurrence is going to tell me the minimum number of changes to transform one string into the other? Any questions about the recurrence? The first thing is to see, is it correct? Okay? And the point is, I got to do something with the right side of my string. It's got to either end on a match, a substitution, an insertion, or a deletion. I try all 4 possibilities. The cost of doing it is the cost of the operation involved, either 0 or 1 or 1 or 1, and the cost of recursively solving the rest of the problem, which is this. My indices have gotten smaller in all of these cases, so I've made progress towards solving it, getting it closer. What would be a basis case for this recurrence? Can anyone give me a basis case for the minimum number of changes to convert the first I characters of one string into the first J characters of a second string? Is there any basis case that you kind of know the answer about without really even looking at the strings? Yeah? If what? You're telling me what is, no, it's called D. I called it D here. What is D of 0, comma n? Okay? Do we know what this is? What does that mean? What does it cost to edit the first 0 characters of S into the first n characters of T? How many changes would I have to do to that? N. Does everybody see that? What does it take to turn something empty into Skeena? Okay, I've got this empty string. I've got Skeena. What do I got to do? Insert, 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 and now you got it matched, right? Does everybody see we've got a basis case? Is there any other basis case here? I claim there's another basis case, yeah? N0. What is D of N0? What is that going to be? What is that going to be? N. Okay? Does everybody kind of get that idea? If you believe in this, we now have a recurrence relation to solve the edit distance problem. Any questions about edit distance, why it's a good thing, and why this recurrence works? Yeah. Am I allowed to modify both strings? Well, what would be the cost of modifying both strings at the end? You know, why would I want to, you know, what would be modifying both strings, the end of both strings do? Turning this into an E and turning this into an A. What's the cost of doing that? Is it 1 or is it 2? It's 2. And what is, I then have to solve this remaining problem, right? Now, if I wanted, if they were the same, I could get the same, if these characters matched before, I would get the same recursive problem at a cost of 0. If they differed, I would have gotten them at a cost of 1 by just substituting 1. There's no reason why substituting both of them at a cost of 2 is going to be a winning move. Yeah? Could we infer that what? So insertions in one string is kind of symmetric to deleting from the other. Okay? That's why I sometimes get a little bit, thumpered on it. I think that the way that we defined it here is all insertions and deletions have to happen to the first string. Okay? That's another reason, I guess, why your problem can't happen. Okay? We're going to have a sequence of changes to the first string to transform it to the second string. Okay? And it doesn't make sense to say, well, I'm going to take the last character, turn it into a 3, and then turn it into a 1, and turn it back to a 4. I'd be better off just turning it into a 4. Okay? Any questions? Okay. Any other questions about this? If you believe that, here is a recursive implementation of that recurrence relation. Okay, and let me see if I can clear the screen enough to do what I want. Boom. See if I can roll this up a little bit. God darn it. Okay. What if my string compare function looked like this? This is a string compare recursive implementation. See, R calls R. Do you see how this string function is, these functions are being called from within this? This is a recursive procedure. What is this going to say? If I equals 0, then that meant the first string was empty. Return the cost of the size of the other string. Does everybody see this? We're given as input strings S and T. We're given the index, the prefix, we want to find the cost of editing the first I characters of S with the first J characters of T. Okay? If I is 0, we want to return the cost of deleting j of the characters, right? If one of the strings was empty, we have to delete the whole other string. If the other string was empty, we got to delete the first string. Does everybody see that this logic is just implementing the basis cases of the recurrence? Okay? What is this logic doing? It's saying, opt is an array I'm using just to keep track of some numbers. It says, what's the optimal cost of ending on a match? Well, match is going to take a look at the last last character of each string and either return a cost of 0 if s sub I equals t of j, or return 1 if they're not equal. If we end on a match, the recursive problem involves two prefixes both shortening. If we end on an insert, it involves that insert was being done so that it would match, insert into the first string was being done so it would match something in the second string. The index went down to j minus 1. And if we delete the last character from the first string, well, the reason we're doing that, after we do that, the first string has gotten shorter. Does everybody see that this is a recursive program that implements the edit distance recurrence? Any questions? What is the running time of this program? Okay, can we do an analysis of this? If I have a string of length, if s is one string is of length s, I guess erase a couple things. If one string is of length n and the other string was of length m, what is the running time of this recursive program? Okay? Yeah? You say n times m. Notice that this is a recursive program and not a dynamic program. Right? This is calling something recursively. You see how this is doing it? This is a recursive thing. What would happen on this recursive thing? What's going to happen? I'm going to start with my first call. And let me throw this one out now. What's going to happen when I make the recursive call? At the beginning, I'm calling it on the full string. S of nm. And what am I going to do? From it, I'm going to be making 3 other recursive calls. Kabunk, kabunk, kabunk. This recursive call was what? n minus 1, m minus 1, n, m minus 1, m, n minus 1, m. Does everybody agree that those are the 3 recursive calls being made? And how many recursive calls are being made from this thing? How many? 3. And how many from this one? 3. 3. Does everybody see? It looks like I've got a ternary tree. What is the height of this tree going to be? Okay. How much? N, or at least n. It's going to start to go away down this big branch. If we take a look at it, the leftmost branch here is going to be n minus 2, n minus 3, dot, dot, dot. By the time we get down after a height of n, we're finally down to something that's going to be 0, comma m. Right? But of course, the other sides can go even longer, because each level is going to knock 1 off of this. You've got a tree whose height is somewhere between n and n plus m of height 3. What is the running time of that algorithm? Suppose the height was n, which is clearly lower because other branches are going to go further. What is the running time of this algorithm recursively? At least 3 to the n. It's something like 3 to the n or 3 to the n plus m. Okay, this is bad news. If you run this thing, this will, just like your program, look great until it hits a wall around n equals 10 or so. Okay? So the recursive implementation of this idea is not going to work. Does everybody agree? This is an exponential algorithm. Yes? Why are we doing what? Why are we doing all three recursive calls? Well, the optimal choice of what to end up, we will end up with either a match, an insert, or a delete. Do you agree that those are the three possibilities? So you've got to try, to find the best one, you got to try all three. Right? How do I know that ending on a match is the right thing? How do I know that ending on a delete is the right thing? The answer is, once I've got the costs, the total costs of what happens if I end on each three operation, then I can go and find which is the cheapest of these and return the cheapest of these. Okay? Any questions? So if you're with me so far, you should believe, yes, this recursive program will work because it's just implementing the recurrence we have, but it's going to be exponential. The key idea of dynamic programming was, why don't we, instead store each of the answers for each of these subranges, okay, in a table so we don't make the recursive calls. That's the idea of dynamic programming. Okay? So here, let's look more closely at the dynamic programming implementation. I am going to build, if I have a string of length n by m, I'm going to build, well, m I'm reusing. Let's say I call it a string of length, let's say big N. This may make it feel worse. Big N by big M. Okay? I'm going to have a cell for every position in the first string, pair of positions with one in the first string and one in the second string. Each cell that I'm going to have is going to encode the cost of reaching this cell, but I'm also going to keep track of a parent pointer. This is sort of a little bit like what happened in shortest path. Remember when we wanted to do shortest path? We found the shortest path to each node, we knew the cost, and we knew where we came from. Okay? We want to do the same thing in a dynamic programming implementation. Okay? What can I do? Okay? So I'm going to build a dynamic programming thing. Let me look at it and then we'll go back and analyze it. This is my dynamic programming program. What am I going to do? String compare doesn't call. Do you see any recursive call here? Is there any string compare in there? There is no string compare in there, right? There is the same basic logic where, first of all, I did initializations. I initialized part of my matrices to the values that I knew. What was my matrix? Well, remember, if my matrix was, again, an n by m, I knew that the cost of editing a zero-length thing into a zero-length thing was 0. Otherwise, it was 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. Does everybody agree that because I knew that the initialization conditions we talked about, that will give me the first row and column of this matrix. Okay, this is now my solution matrix. In general, what am I going to do? In order to fill up M sub ij, what do I need to know to fill up Mij? I need to know what's the cost of, the best cost I would get to edit the first I characters into J characters, where I end on a match, an insert, and a delete. Ending on a match cost what? It was the cost a match or a substitute, depended upon whether these two characters were the same. I need to know, to score whether that was a good idea, I need to know what the cost of, if I end on a match, I need to know what was the cost of editing the prefixes to each other. And this is a smaller value. Mij, it has smaller indices. So it is sitting in the table. If I end on an insertion, one of the indices is smaller. If I end on a deletion, one of the indices is smaller. I've got these three choices. I find which of these three is smaller. That's what this is doing. And I'm going to keep track of which is the minimum cost, okay, of the three choices and what was the operation. Any questions about that? This is just logic to find the smaller of these three. Okay? Any questions? So what is this algorithm going to do? There's no recursive thing, but there are these for loops. What are those for loops going to do? They're going to say, I want to fill up my matrix in a way that I need my cells, the cells I need have to be waiting for me. If I am going to fill up a value, if this was I, and this was J, and this is the ijth cell, what cells do I need in order to compute the value of the ijth cell? What cells do I need to be ready for me? Yeah? I minus 1, j minus 1, which happens to be here if I am correct. Right? Wait, I minus 1, j minus 1 is up here. Right? I lowered I and I lowered j also. Right? This is the one. This cell here is what corresponds to a match. This cell over here is what corresponds to a delete. This was a match cell. This was a delete cell. This was an insertion cell. Does everybody see? In order to compute Mij, I need the three cells around it. And once I've got my initialization, okay, what you see here, my initialization in my matrix, can I safely fill in that thing? The answer is my inner index is J. I think what that means is I'm filling it in like this. Does everybody see what I'm doing? I'm filling in my array, I believe, row to row. And what's great about that? For this cell, notice that the three cells are already sitting there in the array. If I keep walking along the array like this, the three cells that I need have always been computed. And I'm going to go do this and walk through this for the entire array until I filled it in. Okay? Any questions about that? What is the running time of this algorithm? Okay. What is the running time of this algorithm? Well, I ask myself how many cells, and I ask myself how much time per cell do I take to fill it in? How many cells do I have? N times m cells, right? And how much time does it take to fill in each cell? Constant. I'm only looking at 3 other things, right? So this is why edit distance is an n times m algorithm. Remember, back to this other recurrence relation. This was a min not over 3 things, but potentially over n things. That's why the cost per cell was bigger. Okay? Any questions about that? Okay? Any questions about how the edit distance works? Let me show you an example. Okay, let me erase these things. Uh-oh. Let me show you an example here. Kabunk. The Bible says a lot of thou shalt not do things, okay? In modern language, that means you should. Instead of thou shalt, it should probably mean you should. How many changes does it take to get between thou shalt and you should? Okay? Using the dynamic programming algorithm we had before, first of all, notice that the row is increasing from 0 to n. Notice that the column, notice the first column was that. Notice the first row went from 1 to the length. So that you know about. How much does it take does it cost to take thou to an empty string? It would take 4. Okay? And that's kind of what we would expect. In general, what do we know? For any cell in this matrix, let's take an interesting looking cell, kabunk here. That's an interesting looking cell. What do we want to know? In this case, we want to know how much does it cost to edit thou to, it's thou to you should. Right? What are my choices? I could ask myself, does the last character S here match the last character there? S does not match H. So what are my choices? I could either pay 1 plus that cell, which would have been 4, right? Or I could have paid 1 plus this cell, which would have been now 5, which is even more gruesome. Or I could pay 1 plus that cell, which was 2. 1 plus 2 is better than any of those options. So this cell, to get to that cell over here, the logical move would have been to come from there. Okay? And this is why I'm going to keep track of the parent of each cell. Because once I know the parent of each cell, I can later walk back and tell you what the sequence of changes it is. Okay? What's the cost of editing thou shalt to you should? According to this, it is 5. Why is it 5 changes to turn thou shalt to you should? The last change was I substituted a D for a T. That put me up here. That was 1 more than getting to here. How should I change a you should, to thou shall? Well, the L's are the same by following the parent pointer. The optimum thing, it turned out, was to match. And then I've got an A. I now want to match thou shalt to you should. Again, it looks like by the way I did this, the optimal thing was a substitute. I walked backward that way. If so, I turned an A into a U. Now what do I have from here? From here, my optimum move, it turned out, came from over there. Okay? If I delete the O, now I've got you shu to thou shu. And now the H is the same. The S is the same. Okay? The blank is the same. The U is the same. The O is the same. Notice that the costs don't change. Okay, now I've got a choice. What is the best way I can go from here? I guess I've got I'm a little bit confused about where I am now. But according to this, the way I went now was, again, once I do the match of the O to an O, I get back to this cell. What was the way I got to this cell? To get TH into a Y, I can delete the H, that will get me out here, and now I've got a T and a Y, I can do a substitute. Does everybody see that the path back in this matrix defines the sequence of edit changes, okay, of the optimal alignment between the two strings? Any questions about that? Okay. So keeping track of the parent relation, which again, I didn't really show that in the code, but I'll prove to you that I did this, keeps track of which of the three options was of minimum cost. How did I do that? If you notice that when I kept track of which of the three options here had the minimum cost, I not only kept the parent, but I kept the direction that I had gone. I not only kept the cost, but I kept the direction, whether I came that way, or that way. Okay? And by storing that, I can then reconstruct what the path was. Any questions about that? Okay, yes? What is the goal cell? So I always try to write these functions so they're generic and can do a lot of different things. What is this function going to do? This function is going to tell me where is the cell that contains the optimum alignment, the end of the optimum alignment. Now for the edit distance one, what is the cell that contains the end of matching the entire strings? This one. Do we agree? For the edit distance of editing the whole string into the whole string, okay, this is the optimal cell. It turns out for some other edit distance problems, maybe you'd like to learn where is it that the pattern best fits in a long target. Okay? Let's say you wanted to find out where, let's say if the text was the Bible, and you wanted to look for where Skeena was. There are other criteria which says, where is the place in the Bible where this pattern fits best? For that kind of substring matching, which we discuss in the book, and I might discuss next class, I haven't decided, the place where you're going to be interested in starting to walk back is from someplace on this row, but not necessarily the last cell. Right? If in the middle of the Bible suddenly I popped up, then you'd probably want to walk back from here. That goal cell routine is designed to enable me to solve a broader range of problems with the same code. That's why I have it like that. Any questions? So that's a reasonable question. Anything else? Okay, so where are we now? Again, how do you write the program to walk back through the dynamic programming matrix? Okay. This should be something that's sort of like reconstructing the path when we were doing shortest path. How do I find once I have my full dynamic programming matrix with the parent relation, how do I find out what was the sequence of changes that gave me the right thing? The sequence of changes were a path through this matrix. To reconstruct what that path was, we take our cell and we find what was the parent. Parent, 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 parent. Walking back through that parent thing from the end to the beginning. That will give us the sequence of operations that we did. Match, substitute, insert. Okay, delete. Okay? And just like when we were doing, reconstructing shortest paths, okay, from the shortest path spanning tree, there is a simple recursive algorithm that will reconstruct that path. We want the path that goes from the beginning to the end. We know where the end is. How do we print the path out in order? Well, if the parent is the end of matrix thing, we're done. If the parent operation was a match, we're going to find the optimal path getting back to this point, and then output the last match. If it ended on an insert, we go back to the appropriate point recursively and output this search. This is the same algorithm you saw in reconstructing paths from shortest path. Any question? In fact, dynamic programming should smell a lot like finding the shortest path in a directed acyclic graph. It's amazing how many of the problems are kind of that flavor. You're building a matrix, and you want to walk back through that matrix. What are you going to be typically doing? At every step, you're going to be taking the minimum of the possibilities, where you factor in the cost of the last step plus the cost of getting to that last step. Okay? And there is a way of thinking about dynamic programming that it's really a lot like shortest path kinds of algorithms. Okay? So I encourage you to think about that. Okay, any questions about edit distance or shortest path or dynamic programming or anything? Okay, but if you were the kind of person who your program did 45 or better on all of we're able to solve 45 subsets or better for both types of graphs in under a minute, okay? Send me your program. Who am I? I am, okay, again, my favorite email is skiea@cs.stonybrook.edu. Okay, this is what should be in the syllabus. You probably have another email address for me that would also work. But so if you got your programs capable of doing that